2.6 Nash Equilibrium. Games were either IDSDS, iterated deletion of strictly dominated strategies procedure, or the IDWDS, iterated deletion of weakly dominated strategies procedure. Leads to a unique strategy profile, are not very common. How can one then solve games that are not solved by either procedure? The notion of Nash equilibrium offers a more general alternative. We first define Nash equilibrium for a two-player game. Definition 2.6.1. Given an ordinal game in strategic form with two players, a strategy profile S star equals open parentheses S superstar sub 1 comma S superstar sub 2 close parentheses is an element of capital S sub 1 times capital S sub 2 is a Nash equilibrium if the following two conditions are satisfied. 1, for every S sub 1 is an element of capital S sub 1, comma, pi sub 1 of S superstar sub 1, comma, S superstar sub 2 is greater than or equal to pi sub 1 of S sub 1, comma, S superstar sub 2. Or stated in terms of outcomes and preferences, f of S superstar sub 1, comma, S superstar sub 2 is better than or just as good as f of S sub 1, comma, S superstar sub 2 for player 1. And 2, for every S sub 2 is an element of capital S sub 2, comma, pi sub 2 of S superstar sub 1, comma, S superstar sub 2 is greater than or equal to pi sub 2 of S superstar sub 1, comma, S sub 2, or f of S superstar sub 1, comma, S superstar sub 2 is better than or just as good as f of S superstar sub 1, comma, S sub 2 for player 2. Note that in general, the output of the IDWDS procedure is a subset of the output of the IDSDS procedure, not necessarily a proper subset. The game of figure 2.13 happens to be a game where the two procedures yield the same outcome. For example, in a game of figure 2.19, there are two Nash equilibria, open parentheses capital T, comma, capital L, close parentheses, and open parentheses capital B, comma, capital C, close parentheses. We have a 3x3 matrix. Player 1 represents the rows, player 2 represents the columns. Player 1 has capital T, capital B, capital M, capital T, capital M, capital P, and player 2 has capital L, capital C, capital R. The payoffs are 3, 2, 0, 1, 1, 1. That's for the first row across. Then second row starts with 3, 0, 1, 5, 4, 4, and 1, 0, 2, 3, 3, 0. This is figure 2.19, a strategic form game with the ordinal payoffs. There are several possible interpretations of this definition. No regret interpretation. S superstar is a Nash equilibrium if there is no player who, after observing the opponent's choice, regrets his own choice in the sense that he could have done better with a different strategy of his, given the observed strategy of the opponent. Self-enforcing agreement interpretation. Imagine that the players are able to communicate before playing the game and reach a non-binding agreement expressed as a strategy profile as superstar. Then no player will have an incentive to deviate from the agreement if she believes that the other player will follow the agreement. If and only if as superstar is a Nash equilibrium. Viable recommendation interpretation. Imagine that a third party makes a public recommendation to each player on what strategy to play. Then no player will have an incentive to deviate from the recommendation if she believes that the other players will follow the recommendation, if and only if the recommended strategy profile is a Nash equilibrium. Transparency of reason interpretation. If players are all equally rational and player 2 reaches the conclusion that she should play Y, then player 1 must be able to duplicate player 2's reasoning process and come to the same conclusion. It follows that player 1's choice of strategy is not rational unless it is a strategy X that is optimal against Y. A similar argument applies to player 2's choice of strategy. Y must be optimal against X, and thus the ordered pair X, Y is a Nash equilibrium. It should be clear that all of the above interpretations are mere rewording of the formal definition of Nash equilibrium in terms of the inequalities given in definition 2.6.1. The generalization of definition 2.6.1 to games with more than 2 players is straightforward. Definition 2.6.2, given an ordinal game in strategic form with n players, a strategy profile as superstar is an element of capital S, is a Nash equilibrium if the following n inequalities are satisfied. For every player I equals 1 through n. Pi sub I of S superstar is greater than or equal to pi sub I of S superstar ellipsis S superstar sub I minus 1, comma, S sub I, comma, S superstar sub I plus 1 ellipsis S superstar sub n for all S sub I element of capital S sub I. The reader should convince himself or herself that a weak or strict dominant strategy equilibrium is a Nash equilibrium if the same is true of a weak or strict iterated dominated strategy equilibrium. Definition 2.6.3. Consider an ordinal game in strategic form. A player I and a strategy profile S bar sub negative I is the element of capital S sub negative I of the players other than I. A strategy S sub I, an element of capital S sub I of player I, is a best reply or best response to S bar sub negative I. If pi sub I of S sub I, comma, S bar sub negative I is greater than or equal to pi sub I of S prime sub I, comma, S bar sub negative I for every S prime sub I element of capital S sub I. For example, in a game of figure 2.20, for player 1, there are two best replies to capital L, namely capital M and capital T. While the unique best reply to capital C is capital B, and the unique best reply to capital R is capital M. For player 2, the best reply to capital T is capital L, the best reply to capital M is capital C, and the best reply to capital B is capital C. We have figure 2.20, which is a strategic form game with ordinal payoffs. Is a 3x3 grid. Player 1 has capital T, capital M, capital B. Player 2 has capital L, capital C, capital R. The payoffs are 3, 2, 0, 0, 1, 1, 3, 0, 1, 5, 4, 4, 1, 0, 2, 3, 3, 0. Again, that's figure 2.20, a strategic form game with ordinal payoffs. Orange R circle. Using this notation of best reply, an alternative definition of Nash equilibrium is as follows. S bar is the element of capital S is a Nash equilibrium if and only if for player I, S bar sub I is an element of capital S sub I is a best reply to S bar sub underscore I is the element of capital S sub negative I. A quick way to find the Nash equilibria of a two-player game is as follows. In each column of the table, underline the largest payoff of player 1 in that column. If there are several instances, underline them all. And in each row, underline the largest payoff of a player 2 in that row. If a cell has both payoffs underlined, then the corresponding strategy profile is a Nash equilibrium. Underlying the maximum payoff of player 1 in a given column identifies the best reply of player 1 to the strategy of player 2 that labels the column, and similarly for player 2. This procedure is illustrated in figure 2.21, where there is a unique Nash equilibrium, namely the ordered pair capital B, capital E. Figure 2.21 is a strategic form game with ordinal payoffs. It is a 4x4 grid. Player 1 has the rows and has strategies capital A, capital B, capital C, capital D. Player 2 has the columns with the payoffs capital E, capital F, capital G, capital H. The payoffs are 4, 0, 3, 2, 2, 3, 4, 1. Then next row 4, 2, 2, 1, 1, 2, 0, 2. Next row 3, 6, 5, 5, 3, 1, 5, 0, 2, 3, 3, 2, 1, 2, 3, 3. In exercise 2.3 in this section 2.19 explains how to represent a three-player game by means of a set of tables. In a three-player game, the procedure for finding the Nash equilibria is the same, with the necessary adaptation for player 3. In each cell, underline the payoff of player 3 if and only if her payoff is the largest of all her payoffs in the same cell across different tables. This is illustrated in figure 2.22, where there is a unique Nash equilibrium, namely open parentheses, capital B, comma, capital R, comma, capital W, close parentheses. We then have figure 2.2. It is a 3-player game with ordinal payoffs. There's two 2x2 grids, and the first 2x2 grid has player 1 on the rows, player 2 on the columns up top, and player 3 columns on bottom. The same order goes for the second 2x2 grid. In the first 2x2 grid, the payoffs are 0, 0, 0. Then 2, 8, 6. Next row, 5, 3, 2. Then 3, 4, 2. In the next 2x2 grid, again with 3 payoffs, we have 0, 0, 0, 1, 2, 5, 1, 6, 1, 0, 0, 1. Again, that's a 3-player game with ordinal payoffs. Unfortunately, when the game has too many players or too many strategies, it is thus impossible or impractical to represent it as a set of tables. There is no quick procedure for finding the Nash Equilibria. One must simply apply the definition of Nash Equilibrium. This is illustrated in the following example. Example 2.1, there are 50 players. A benefactor asks them to simultaneously and secretly write on a piece of paper a request, which must be a multiple of $10 up to a maximum of $100. Thus, the possible strategies of each player are $10, $20, ellipsis, $90, $100. He will then proceed as follows. If not more than 10% of the players ask for $100, then he will grant every player's request. Otherwise, every player will get nothing. Assume that every player is selfish and greedy, only cares about how much money she gets and prefers more money to less. What are the Nash equilibria of this game? There are several. Every strategy profile where 7 or more players request $100 is a Nash equilibrium. Everybody gets nothing and no player can get a positive amount by unilaterally changing her request, since there will be more than 10% requesting $100. On the other hand, convince yourself that a strategy profile where exactly 6 players request $100 is not a Nash equilibrium. Every strategy profile where exactly 5 players request $100 and the remaining players request $90 is a Nash equilibrium. Any other strategy profile is not a Nash equilibrium. 1. If fewer than 5 players request $100, then a player who requests less than $100 can increase her payoff by switching to a request of $100. 2. If exactly 5 players request $100, and among the remaining players there is one who is not requesting $90, then that player can increase her payoff by increasing her request to $90. We concluded this section by noting that since so far we have restricted attention to ordinal games, There is no guarantee that an arbitrary game will have at least one Nash equilibrium. An example of a game that has no Nash equilibria is the matching pennies game. This is a simultaneous two-player game where each player has a coin and decides whether to show the heads face or the tails face. If both choose capital H or both choose capital T, then player 1 wins, otherwise player 2 wins. Each player strictly prefers the outcome where she herself wins to the alternative outcome. The game is illustrated in figure 2.23. It is the matching pennies game. It is a 2x2 grid with player 1 on the rows, player 2 on the columns. Each have the set of choice strategies that have as capital H and capital T. First quadrant 1, 0. Second quadrant 0, 1. Third quadrant 0, 1. And fourth quadrant 1 and 0. Test your understanding of the concepts introduced in this section by going through the exercises in section 2.9.6 at the end of this chapter.